Okay, so let us start remaining topics of wave optics and we can cover up. So we have discussed about double slit YTSC. Some important point in YTSC we'll discuss today. So one of the thing is that in YTSC, if you consider this width also, this width is B. Let us say this width is B1 and this width is B2. So how does this V1, V2 affect the intensity of this slit? Because this slit is S1 and this slit is S2. So this intensity which it is emitting is I1 and this intensity is I2. This I1, I2 are the intensities of the sources. So if you change the slit width, it affects the intensities. So here we need to note that these intensities are proportional to the width V1 and this intensity I2 is proportional to the width of the equal. Okay, so this intensity is proportional to width of the slit. Why it is like that? Because once the wavefront is coming, how much portion of the wavefront is exposed here? That is what it is. How much portion of the wavefront is coming? So here we have taken that rays are coming parallel like this way, right? Rays are coming parallel like this way. Rays are coming parallel. So if parallel rays are there, so wavefront or like flat wavefront will be there, flat wavefront or plane wavefront. So depending on how much portion is exposed here, how much portion of this wavefront is exposed, based on that only intensity will be calculated. So if the width is more means more exposure will be there, less means less exposure will be there. So that is what it is. Intensity is calculated based on right. So how does the intensity affect the calculation of intensity on this screen? Okay, these are intensities, but in the superposition when happens, interference when happens. So let us take for example the maxima point. This is central bright fringe, then first bright fringe, then all those bright fringes. So bright fringe intensity formula, it is like maximum intensity formula. So the formula for resultant maximum intensity is root I1 plus root I2 whole square. Okay, that's the. Suppose if I consider that one example, let us take. Suppose initially the widths are same. Both the slits have same width. So they have same width as BB. Let us say. So their intensities I1 and I2 will be equal. Let us write as I1, I1. So this resultant intensity of the maximum becomes 4I1, right? Because it becomes 2 root I1 whole square, so 4I1. Now suppose if I try to change the width, let us say I make one of the width as double or one of the widths is smaller. Suppose I reduce the width of this slit as B by 2. Other width I am keeping as same as B. Now what happen? Intensity will also become half. This become I1 by 2. This will become I1 only, right? So now if I try to calculate now resultant, this time let us say densities. So root of I1 by 2 it will be, and here it will be root of I1 whole square. So how much it will be? You have to take root I1 common, so that will become I1 only, and this will become 1 by root 2 plus 1 whole square, right? So if I consider this, then this will become I1, square it, so 2 will come here, this factor uh, 1 plus root 2 whole square, 1 plus root 2. You can further simplify this, but this is how intensity will change. So if they ask ratios of intensities, so final intensity ratio by initial intensity maximum ratio, that is 1 plus root 2 whole square by 2, this and that is 4. So this will become 1 plus root 2 whole square by 8, right? So that's what it will come. This intensity ratios will come by this. Okay, that's what will happen in this case. Resultant intensity ratios. So previously the maxima and now the maxima ratios of the maximum intensities is becoming 1 plus root 2 square by 8. We can further simplify, but let it be. You can calculate it. Clear? That's what it will get. Then this idea of intensity, how it get affected, we should know that. Then let us go next further. Now we are going into the next topic of diffraction. Let us go single slit diffraction. There are Fresnel diffraction and Fraunhofer diffraction. The single slit diffraction that we are discussing, it is Fraunhofer diffraction. Okay, not Fresnel. Fresnel is different. That is not in syllabus. Okay, so here what happens is that there is a single slit here like this. Okay, and from this single slit, and this is the screen here. The screen is here, and this width is B. Width of this slit is B, and what happens is that from here, so many points on this, because when the wavefronts or light is coming, so note that here light will be coming like the same way parallel rays are coming and hitting. So when parallel rays are coming, these parallel rays are coming, so the wavefront of that parallel rays will be hitting it like this. So this portion of the wavefront which get exposed here, this portion of this wavefront which get exposed to this slit, here every point on this, every so many points will be exposed on this wavefront. So all these points acts as a source of light. You know that again wave model we have seen that each point behaves like a source. So each point will start emitting its own secondary wavelets and all that. So any point on this screen. So first of all, let us say this is the central axis origin. Now any point here, if you take P at a distance of y here, right? So you need to take waves coming from all these points and merging here like this. All these points waves are coming here and now. So now these waves are going to make superposition, and that point will have maxima minima. So we want to first find out, let us say that is maxima happening. So what is the distance y for maxima to happen on the screen, right? That distance we want to calculate. So first let me give you the formula. Derivation I will do afterwards. Okay, derivation will little maths it will require. It's not given in the book. Most of the textbooks they have just given formulas. Even in NCRT they have given formulas for this. For double slit they have derived. Single slit they have not derived. Some logics they have used. Some analysis they have used without going into maths. Okay, but I will go into the maths. But first let us write the formulas. Okay. So the formula for maxima, and this distance is d, distance between this and this. So for maxima, uh, for maxima the formula is y is equal to n plus half lambda d by d, and for minima the formula is y is equal to n times lambda d by d. Okay. Remember, this is the nth order maxima. This is the nth order maxima. Similarly, this is the nth order minima. Nth order for nth order minima for nth order maxima. That's the formula. Here you see the formula has become just the reverse, right? Why it has become like this? Did you cover in your class, Sam? Okay, but let me derive this now. First, this formula is there, and here derivations of this are also. But angular width also note here what is called angular width. Angular width means if I take this center line or this line will be making angle theta here with x-axis. So this theta is called half angular width. It's called half angular width. Half angular width. Okay. So this half angular width, because this is very large distances, so this theta can be written as tan theta. Just tan theta or theta is sufficient. This theta can be written as just y by 2. Half angular width. Full angular width means 2 theta. 2 theta means 2y by d you can write. So suppose I want to calculate for maximum this half angular width. So what is the ratio of y by capital D? Here itself you can write, isn't it? Here itself you can write. Y by D ratio you have to write. So if I write theta y by D, so y by D will become n plus half lambda by D. Here also if I write theta y by D become n lambda by D. Right? So that's quite easy thing to write. So that's what is half angular width. Full angular width means total we have to take, because maximas happen this side also, this side. Okay, both sides maxima happen. So suppose if I take first maxima here and here, so it will be subtending theta this side, theta this side. Total angle will be 2 theta. Okay, so 2 theta is total angle, full angular width, right? So this we have to be. Now let us understand how actually happening. So to understand this derivation, we need to understand one important thing, that vector addition we should know. Vector addition you know already. Suppose we want to add vector. So here what happens is that in between these slits that are there, and this is the screen. So we want to divide this into small points like this. Okay, the small points like this. Each of these points are acting like a source. Okay, they are acting like a source, and let us say that this distances between them is very small distance. So suppose total distance is b. Let us say total distance is b between the slit. So I want to divide them into very small gap. It is like a slit only. So this I am going to divide it by n number of parts. So let us say it is b by capital N. Each gap is where number n is very large. Okay, because if you are going to divide into continuously so many slits, then each gap between them is b by n, b by n. Are you understanding? Where n is the number of slits, we can divide 2 also. Suppose this entire gap I can break into this entire gap b, I can break into b by 2, b by 2. Correct? B by 2, B by 2 also I can. Then that means I am considering here like this is one slit, this is another slit, right? So here I am dividing so many. Capital N is like the number of slits we are taking here. Capital N is the number of sources or slits between the original slit. So this original slit whose width is B, we are dividing into small slits. Okay. Now each of these slits is sending the rays here, right? Each of these are sending its own rays here. So suppose if I consider the first slit, so these 2 points, if I take from this point and this point, see these 2 rays I have made. These 2 rays I have made from these 2 points which are separated by distance of b pi n, right? B by n, they are separated from this. So here these waves, these are like first wave. Okay, note that this is like first wave, this is like second wave, right? And these two waves are having some path difference. This is wave. Okay, how do you write wave? You know that y is equal to a sine kx minus omega t plus phi 1, or let us say here initial phase is 0, let us say, right? So next one will have a sine kx minus omega t plus, let us consider phase differences between them, equal phase differences will be there between them. So total phase difference is something, let us write some phase differences between them will be there. I am writing this phase differences delta phi delta phi. Okay. Similarly, next one will be there. Next wave will also come, that will have 2 delta phi from original, because they are separated by equal distances. So there will be equal path difference, equal phase difference. Okay, right? Like this it will come. So many such things will be existing here. So now let me show you about that small points which is like at a distance of d by n, and this wave we are going to take here. Okay, here we are taking this interference. Now um, this distance, and now how did we do in a double slit experiment? Same way we'll be taking it like this part difference. So this is what is the part difference. This angle is small angle theta, so b by n sine theta. This is the small path difference delta x, right? This is the path difference here. And due to this path difference, there will be phase difference, right? This is small path difference we are taking. Due to this, there will be small phase. That phase difference is delta phi only. So this delta phi phase difference is 2 pi by lambda into path difference, right? So if I substitute that, we will get this as 2 pi by lambda into b by n sine theta. That is the phase difference delta phi delta phi. Okay. Now how to add these waves? Because we basically want to add these waves. An addition of waves is like a phasor addition, right? Phasor addition. So phasor addition, we have to understand phasor addition here. Phasor addition we have to understand. So first of all, you need to understand that each of them has same amplitude. Each of these small slits that we have broken into, each of these small elementary slits have same amplitude because it has the same width. Now here it's a very important conclusion that we have to make, or you can say assumption you are assuming. It's a very important assumption of this theory. The assumption is that this each small slits have some amplitudes of wave coming from each small slit that is proportional to this width of this slit. Here intensity we are not taking, we are taking amplitude. So each small slit is giving a wave whose amplitude is proportional to b by n. B by n, B by n, B by n, B by n. Each has equal amplitudes. So let us try to first add that. And first note that I want to suppose add this amplitude. This amplitude is A naught. Then this amplitude is A naught. Note that each of them has the same phase difference of delta phi. Then from this direction we have another next wave have amplitude in. It's like a polygon law. We are going to apply that. Okay. So A naught, A naught, A naught, A naught. This idea that we are going to add is n number of vectors you are adding. Okay, if you have only two factors, then you can add factor formula addition. But we have so many n number of slits are there. Each slit is like a source. Each slit is giving its amplitude. That amplitudes are equal, and we are doing the addition of that. And each has same phase differences. Next wave, next wave, next wave, next wave. They have equal phase differences. Okay, so this wave, second wave have phase difference delta phi from first wave. Next third wave has same phase difference delta phi from second wave. So like that it will be going on. Okay, and we want to add all these and let us say they are going to come on, like last one is this one, a naught. This is also last a naught, like this. So when you want to add now, it will be like a polygon law like this. This will be like resultant intensity. Okay, resultant intensity. I have not shown all that dot 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 you can do. But one important thing is that all of this is going to lie on a circle by symmetricity. So addition of this can be done by understanding that they are going to lie on a circle, a very very large circle like this. Okay, they will be lying on a circle. They will be lying, and the center of circle may be somewhere else. We do not know. So this is what is the resultant. Resultant is like a chord of this circle. Chord of this circle. Okay. But one thing we have to note that when you join this, right, this total angle is going to become n delta phi. N delta phi, because the angles delta phi, delta phi, delta phi, delta phi, total deviation is actually n delta phi, which is at the center. Okay. So now, first of all, you should know very important result. I will tell the important result of chord length. Chord length formula, I think you know. Chord length formula you should know. Suppose there is a circle of radius r, okay, and I want to find chord length. And suppose these angles are equal as theta theta, okay, or take total angle as theta. Total angle is theta you take. So this is theta by 2, theta by 2, okay. Total angle is theta. This chord is subtending theta angle, so half angle theta by 2 theta. So you know this length, right? Because this is perpendicular here. This is perpendicular. Perpendicular divides the chord. So how much is this length by trigonometry? This length becomes r sine theta by 2. Similarly, this length is also r sine theta by 2. So what is the chord length? Chord length becomes 2r sine theta by 2. You know this, right? Chord length formula. So if there is a circle and there is a chord with subtend angle theta at the center, the chord length is 2r sine theta by 2. Very simple. So same thing is here also. The chord length AR can be written directly here because AR is anyway chord length. So this resultant amplitude chord length is using the same formula, 2 times radius into sine of total angle is m delta phi by 2, right? That's the important equation. This is the important equation. Similarly, if you look at each of these small, no, each of this is small chord, you look at this small chord. This small chord is actually subtending equal angle, and these equals angles are delta phi, delta phi. Each of this chord is also subtending equal angle as delta phi, delta phi. Now, if I write each chord length also I can write. So, each chord length, if I write A naught, that becomes 2r sine of delta phi by 2. It's a very important equation. Then let us now divide these two. Let us divide these two. So, AR by A naught. If I divide 2r will get cancelled. So, sine of n delta phi by 2 divided by sine of delta phi by 2. This ratio we got, so we can say that the resultant amplitude AR is equal to A naught sine of n delta phi by 2 divided by sine of delta phi by 2. Right? And what was A naught? What was A naught? A naught was the amplitude of that. A naught was uh, amplitude, I think. Individual slit amplitude. Correct? Individual slit amplitude it was. Hmm. Hmm. Okay. individual amplitude. Now suppose if I consider that this entire slit which has having the width b, this entire slit we have broken into small slits of width b by n, where n is the number of elements that we have divided. So the amplitudes coming through each of these was a naught a naught. That a naught was proportional to b by n. Now suppose from the total slit, the amplitude coming is a. So that total amplitude A is also proportional to B, right? So now if I take this ratio A naught by A, I can write this as 1 by n. So A naught can be written as A by n. What is A? A is the amplitude for the entire slit. A is amplitude from the entire slit. Okay. So let us substitute A naught here. So that resultant amplitude becomes equal to A by n sine of n delta phi by 2 divided by sine of delta phi by 2. And note that this angle delta phi is very small because it is the phase difference between these two waves, and a number of slits is infinity like that. We have taken very large number of slits because these are like elements. So we have to consider that sine. Now we can do approximation because this is a very small angle. So here we can write it. Here we can write that sine as same as that, right? So this AR now we are writing as A. This numerator we cannot do anything because that angle may be a large angle. But denominator we can do this small angle approximation. So delta phi by 2, and this n I will combine it here. Okay. So that's what we are saying, that the amplitude of resultant wave in single slit is given by this formula. It's an important formula. Now we can calculate intensity because intensity is proportional to amplitude square, right? So this entire slit giving intensity I, let us say, which is proportional to A square, and the resultant intensity is proportional to AR square. So now if you take the ratio of this, so IR by I becomes equal to AR square by A square, or AR by A the whole square. So now if you take this ratio, what do you get? Take this ratio. So IR by I becomes equal to this, by this ratio will become sine n delta phi by 2 divided by n delta phi by 2, this entire whole square, right? So that's why the final resultant intensity at a point will be intensity of the entire slit multiplied by this factor sine n delta phi by 2 by n delta phi by 2, the whole square. This is the formula for intensity formula, resultant intensity formula due to superposition. Now we will try to calculate maxima minima conditions. Maxima minima conditions we calculate. So for maxima, what happens? For maxima intensity means this has to be maxima. So this sine of this has to be maxima. So for sine of this n delta phi by 2, what is the value of this? This n delta phi by 2 should be 90 degree, correct? 90 degree, because sine 90 is 1. So that means we are going to take this as pi by 2. Let's take this as pi by 2. And what was the value of this Hmm. Delta phi was how much? And delta phi, that will come afterward. 2 you can cancel out. Delta phi was what? Initially we have written delta phi. So, and this small delta phi we have written. Remember that small slits that we are breaking into this. This was length d by n, and then we have taken path difference. You remember this? This path difference become b by n. Uh, this angle was theta, so b by n sine theta we have taken. Correct. This path difference was delta x, and from this path difference we have calculated phase difference delta phi 2 pi by lambda into delta x. So 2 pi by lambda into d pi n sine theta. This is what it is. Let us substitute this here. Yeah. This is what is delta phi. So 2 pi by lambda d pi n into sine theta is equal to pi. So n factor get cancelled and pi also get cancelled. So 2b sine theta comes as lambda. Correct. 2b sine theta comes as lambda. So what is b sine theta comes? B sine theta comes as lambda by 2, right? So here I think we have taken the condition. Uh, remember this condition we have taken pi by 2 because we have taken sine we wanted maximum, so the angle should be 90 degree. Correct, right? Angle should be 90 degree means angles become 90 degree at many places. No, sine it becomes 90 degree also and 270 degree. Correct. Odd multiple of pi by 2 it happens, I think. Correct, right? So we can write pi by 2 might be, we can also write as n plus. I think in general, if you want, you can write this value as n plus half, n plus half pi by 2. You write it because n is 0 means no pi times multiplied. Okay, so and if I put 0, so pi by 2, and I put 1, 3 pi by 2, like this it will happen. So in that case, what happens is, um, okay, so here 2, if I take LCM and 2 I get cancelled, then it will become 2n plus 1. This will become 2n plus 1, right? Pi also got cancelled. Pi got cancelled, right? So then it become lambda will come and 2n plus 1 will come. So this is what it is. So here d sine theta is coming as n plus half lambda. This is the condition for maxima. Remember, these are maxima conditions we are calculating, and now you can take this theta is very small, right? So this is like y and this is like d. So this is what is theta. So theta sine theta same as theta. So y by d we are writing. So n plus half times lambda. So from here, that's what the result comes as n plus half lambda d by d. No teacher will do this derivation because they have this is not given in the book also. They may say something logically as NCRT has done to skip the hard work, but NCRT has not done that. Okay, and so in most of the textbook it is not given. Right, so that's the formula. Similarly for minima formula, if you want, so you see minima formula means sign has to be 0 here, minima. So 0 condition means n pi you have to put it here for minima. So in delta phi by 2 you put n pi, okay, for minima, and you will get the result for minima. You can try that. So for minima n delta phi by 2 should be n pi. So from here now you substitute n by 2 delta phi formula here we have written 2 pi by lambda b by n sin theta is n pi. Pi pi get cancelled, 2 2 get cancelled, n get cancelled. So from here you get b sin theta as n lambda. Again sin theta is y by capital D is n lambda. So from here the condition y is equal to n lambda d by b. This is the result for minima. Remember this result is for nth order. Nth order minima. Thus this result is for nth order maxima. Order remember. Nth order maxima in single slit experiment. Okay. So this is the main formula. Once you know that, most of the calculations can be done here. Right? The angular width is same. Angular width means theta. Theta is y by d. That also you can calculate. Here also you calculate theta. Y by d. Y by d means n plus half lambda by b. Half angle. Here also minima. That theta is y by d. So n lambda by b. Okay, so we can calculate half width also, full width also, distance also. Now here important thing to note is, very important thing in single slit experiment is like the spot radius of a spot. So if this is B and this screen it is, and first minima, the minimum formula, remember minimum formula is, this is suppose minima, suppose if I say this is first minima, so this side also first minima, central maxima will happen here. This is central maxima will happen here. Okay, so first minima condition, as I told, that y is equal to n lambda, n is 1, so lambda d by b. This is what it is, first maxima, sorry, first minima. So this is first minima, so this distance is lambda d by b. So actually what happens when light comes here, there is intensity formation happens like this way. So this looks like this as the bright spot. This entire is called bright spot. So here like a disk is forming, bright spot is forming. So this is like the radius of that bright spot. Okay, this note that this y equal to lambda d by d. This is the radius of the first bright spot. Radius of first bright spot or central bright spot. Central radius of central bright spot. Most of the calculation comes from that only, radius of that. Or sometimes they may ask what is this angle theta, angular width of this. So this angular theta is y by capital D, which is lambda by d. This is the angular width. Full angular means total angle 2 theta you calculate. Okay, so that's how we calculate. Most of the calculations comes on this. Hmm. So remember that formula and do the calculation of bright spot. Generally questions of bright spot will be coming. Hmm. That's what it's in the set. And if you look at the intensity, now this is very important. Intensity, if you look, this first minima is there, right? And there will be maximas also. So maximas, all intensities are not same. So intensity distribution is non-uniform. Intensity distribution, intensity distribution in single slit diffraction. This is the last topic. With this we will cover that. So on this script, if you take 0 and then you take minima, maxima, like that. So maxima, let us say first maxima. Okay, here also first maxima, then second maxima, here also second maxima. In between there will be minima, so first minima, here also first minima, second minima, here also second minima. So how does the intensity pattern look like? So first you look at this pattern. This is the central bright spot. After that, what happens? This bright spot decreases in size. So between the first and second, this is going to become smaller, not the same size, smaller size. Okay, this side also symmetric it will be like this. Okay, not the same size like this. After that, it is next is going to further decrease. Next will be further, it will decrease like this. Okay, so you see this, the first one, that is the central bright spot, it is the maximum. This is the central maxima, all others are called secondary maximas. Okay, so these are called secondary maximas. Secondary maximas. These things also secondary only. These are all secondary. Secondary maximas. This is what is central maxima. Central maxima. Okay, so here we need to note important thing is that intensities are not same, but in YDSC all had same intensity, all maxima had same intensity. Here all maximas do not have same intensity. So you may ask like what are the values of these intensities of these maximas, right? So I just give you the value of it intensities. Maybe you can just note it because the proof is not there. Already we have proved it, but we need to calculate from that diagram. Okay, so I just give that value of that. Maybe we can just note down the values of those things. Okay, so here the first intensity, if I suppose the first intensity is I naught, suppose if I say the first central intensity maxima is I naught, then this next maxima comes as I naught by 22. Okay, next maxima comes as I naught by 22. Then for the third maxima, intensity becomes I naught by 61. Same this side also. This become I naught by 22, and this become I naught by 61. So the maximum intensities of secondary maximas are smaller and smaller. Like that it happens. Okay? Decreases. How do we know that? We know actually from this derivation that we have done. Where that derivation is from? These derivations, right? Where it is? Yes. No, no. After that we have derived that intensity formula that we have written sine of and delta pi whole square by that, right? In that formula, it is that if we substitute the values, we will be able to calculate that. Okay, it is there on. Okay, so we will be able to find out. So let us wind up this session. So the next class further we can continue next and we can solve any doubt. Do you have any doubts also? Okay, so let us continue in the next session. We'll cover up the doubts. Okay, fine then. Thank you. Bye bye, Sam. Good night.